Hi, everyone. Welcome to the Open Simon webinar series. I want to make sure that I'm heard first and foremost before we go forward. So if someone could either come off mute or text in the chat that you can hear me, that would be really helpful. Thank you so much. Oh, appreciate it. Well, welcome, and I'm glad you were able to join us today. We have a great presentation today for you guys. We have Kim Larson here, who's a learning engineer with the Open Learning Initiative and the Simon Initiative. And we have Ken Koedinger, who is an expert in this learning curve business, but also a professor in our Human-Computer Interaction Institute and director of Learn Lab and director of our Metals program here at Carnegie Mellon University. So welcome. Going to turn this over to Kim.
Hi, everyone. As Erin said, my name is Kim Larson, and I'm a learning engineer with the OLI Simon team. And today, I'm going to show you a way that I use data to make iterative improvements in a course. One thing I'm looking to see is whether there are parts of the course, specifically knowledge components or skills, that students are struggling to learn and why. And are there questions that are hard? And that might not be a bad thing because the learning objective itself might be hard. But what I'm looking to see specifically are cases where students are making progress on questions, and then all of a sudden there are certain questions where they don't seem to be doing as well as they were on the earlier ones. And so what that could mean is that we might be showing them another skill or concept that we're not actually teaching them. So what learning curves allow me to do is find those instances, and that often leads to ways that I can improve the assessments in the course. Now I'm going to show you how I did this for a graphical causal modeling course in OLI. So first I want to orient you to the graph. The one on the left-hand side is for the knowledge component. Distinguish when two variables are adjacent or not. And what I want to first let you know about the graph is the x-axis shows the number of opportunities and the y-axis shows the error rate. The red line represents real student data and the blue line is the prediction. So as I started to mention, on the left-hand side, we have a knowledge component that is a good learning, that shows a good learning curve. It's smooth and declining. It also shows that it's a good model fit with the data. And then on the right-hand side, we have a flat learning curve for the knowledge component, categorize a variable on a path as a collider or non-collider. And as you can see, it has a poor fit with model with the data. And so the other thing to look at specifically here is there's a big spike at opportunity 4, which suggests that there was probably an issue with a question associated with this data point. So when you're in Datashop, you can actually click on that data point and you're able to access a couple of things. One is you can look at the question and you can also look at the error report. What I'm first going to do is show you the question just so you can see what it looks like in OLI. And here we have the graph and the question. One thing to note is in the learning curve example I showed you, the first data point was a different question than this activity, which has 4 questions. So the offending data point where we saw the blip is actually the 3rd question here. So I just wanted to point that out first. So now I'm going to have, we're going to take a look at the error report. And if we look at this, we can see that that first question for X1 variable, students are doing very well on. They're going to, there's 81%, almost 82% of people are getting it correct. And then on the other one, the X3, where we saw the blip, we notice it's only about 36%. So what I want to do next is I'm trying to figure out why identifying whether X3 is a collider on a path from X1 to X2 to X3 to X4 is harder than identifying it for X1. And so looking back at this, I also pulled in the immediate feedback that the student sees after each response. And one reason we can see that X1 only has one edge connected to it. So that is probably one reason why it might be a little easier. In fact, X1 and X4, if you'll notice, give different feedback than X2 and X3. X1 is talking about variables with only one edge, and X2 and 3 are talking about mediators. And right there, I can immediately tell that we're talking about a different knowledge component that's required here. But what's even more nuanced in this reason that X3 is so much harder is that what we say here in the feedback, you can see, is that X3 is not a collider because it has two edges pointing into it. But if you'll notice, it looks pretty clear that two edges are pointing into the variable X3. But what we didn't say was that specifically on the path X3, from X1 to X2 to X3 to X4, and not on the path from X1 to X3 to X2, where X3 is actually a collider. So as a consequence of this, what we decided to do, myself in a combination with the instructor, is we decided to relabel those as two different knowledge components. And of course, after doing this, we didn't have enough practice opportunities for students, especially for the harder one. So we went and we dug into this even further. We have an instructional video that students look at. It's only a couple minutes long prior. And what we realized is we not only were not giving them practice on mediators, but we weren't giving them practice on common causes and common effects on a path as well. So we added questions for all of these different variables that all these different roles that a variable can play on a path. And so now what we've done is we've added these extra questions and we're running the course again, and we'll get feedback, or we'll get data back, and we'll be able to take a look at those learning curves and see if we were successful once we found that we were actually assessing the students on different knowledge components than we thought we were.
Thanks, Kim. That was great. So I think what that really showed is how you, is the thinking that goes into using the learning curves to diagnose a problem that you see, right? And then dig in and try and figure out what that problem may be. And in this case, this is a question that's in a, what kind of course again?
It's the graphical causal modeling course.
Right.
And while this course, you may not be familiar with the domain, you will be on a course that you're working in. And so it'll be a little easier to distinguish where you might have a different knowledge component.
Right, right. So I'm wondering, I know you guys had questions about the question itself and the example that Kim was going through. Are there, do you have questions about the learning curves that she showed? And let me go back to those.
Yeah, I will say, this is Ken Koedinger. One of the challenges we have in illustrating this idea is, you know, sometimes we use simple examples like from high school mathematics, and then people say, does this just work for math?
Right.
And so what we tried to do this time is Kim's using a real example from a real college level course where, you know, she really went through this process and discovered something, a flaw in this particular course. And, you know, we could talk more about the details of what this concept is in this course, but the more general point is that you can use a technique like this to identify places where students are being challenged by, you know, some hidden skill or concept is needed that wasn't sort of apparent in the original design. In the original design, all these questions were meant to be getting at the same thing. What is the collider? Well, it turns out it's much easier to answer that in certain circumstances than others. And if we really want students to understand what is a collider, they have to be able to answer it, especially in the hardest circumstances. And so we didn't know which were the harder ones and which were the easy ones, or even that they were that much different before we had this data. Now we do. And now we can drill down and focus on this. So I hope that helps, but we definitely want to make this interactive. So if you have other questions, please jump in. It's also possible that we could show an example from a domain where the content is maybe easier to get one's head around if that was desirable.
How are you guys feeling with this example? Would you like another example? Or do you have questions about learning curves in general and how you would dig in? Or even if you have an example that maybe you're struggling with.
I think we're small enough that if you want to jump in on audio, feel free.
Yeah.
Hey, Vasu here. Yeah. Hey, Ken.
Hi.
Hey, sorry, I just mistook the graph that you showed to be, a graph that we get from LearnSphere. So never mind. No, you're good. Yeah, please get it. I'm okay. Don't worry.
Okay.
Great.
Is there someone else? Or?
Yeah, so I was just trying to interpret the graphs that we're looking at on this slide right now. So then is this spike that we're seeing at opportunity for the question on the next page?
It was it's the X3 question asking whether it was a collider or non-collider, whether that variable. Okay. As I kind of went through it kind of quickly. The first data point is actually a different question. This activity has 4 questions, but it is actually the third question in this activity that is the 4th data point that shows the blip. Kind of hard to explain there, but.
Right.
In general, sometimes, like you're seeing multiple instances of the same question kind of within the same problem stem. But in general, this particular concept may be seen across multiple different questions. And indeed, in this course we're just drilling down on one of them.
And there are other graphic representations, which we actually made more complex examples to try and get at the places where people were confused when more than one edge was pointing into a variable.
So how many of you have been in Datashop? Maybe give me a text. I don't have a poll this time. Okay, I've used it. Great. I haven't really used it. Okay. Well, here, I'm going to stop this share and share with Ken, who's gonna.
Yeah, I'll give a little bit of a Datashop demo so you can see it more dynamically and take the risk of doing a live demo. Hopefully everything runs smoothly. But first I have to operate Zoom properly. Where is my share? Good. Oh, you're still sharing.
I thought I gave up my share.
No.
Stop share here.
Thank you.
Yeah, I was gonna say I can still.
All right. So in 1 second, I hope you see an entry screen for Datashop. When you go into Datashop, I skipped the login. We can help you with that if you need. But one of the things we have here on the front page is this, what can I do with Datashop? And you can self-identify as your role. And if you pick one of these things, you'll get some topics of interest that are our best guess for what topics that role might be interested in. And I'm just going to click on one of these randomly, like test an instructional principle. And this indexes into a series of descriptions of different things you can do in Datashop. And then it shows related data sets and papers that have been written about those data sets. So if you just scroll down this, I guess this was the one I was looking at. You can see like there's some data sets about Chinese vocabulary, and this contiguity one is about diagram use in geometry. And here's one, stoichiometry is in chemistry, another one in Chinese. REAP, I think, was English as a second language. This one's about physics. There's a couple data sets about physics. And there's some associated papers here. But what I'm going to do is, we have a data set that is a nice one to illustrate how Datashop works, because the content of it is a little bit less challenging than causal inference, and maybe more familiar to most of you. I'm going to go to that. I'm going to try to go to that data set. That menu at the top is being slow for me for some reason. There we go. And I'm going to click on this learning curve tab and select all the data. You can have different samples of the data, for example, if you want to looking at different populations. And over here are different ways of tagging the very same data with different hypotheses about what the underlying skills or concepts are. And when we first released this geometry cognitive tutor into our high schools, the original model had these 15 concepts or skills. We call them knowledge components, kind of generalize across concepts or skills. And they may look familiar, like finding the area of a circle is circle area, and circle circumference, and circle diameter. And what this graph here of all selected knowledge components shows is that averaged across every student and every knowledge component, what's the error rate on the very first opportunity every student had on every knowledge component? It's about 45%. What about the second opportunity? It's about 33%. So it's tending in that red line there to go down, right, with successive opportunities. And that looks good. So you might say, yeah, my course is really working well. The more students get practice, the better they do. But if we look at individual curves for individual these knowledge components we've hypothesized, we can see that while a lot of them individually look decent, so-called good here, some of them have some issues that might suggest reasons to improve the course. So any one of them that's low and flat are situations where the error rate was already pretty low right from the start. And particularly if it's long and low and flat, you might be having students essentially engaging in a lot of busy work. So one intervention you can do is find low and flat curves and reduce the number of activities associated with them. So that's a simple one. Another thing, what Kim saw is she saw one of those knowledge component curves in this no learning category, essentially because, as you can see here, the error rate's not going down over time, over opportunities to practice. It's jumping up and down all over the place. And as she illustrated, you can drill down on one of these, and Datashop will show you which activities are being averaged in this particular situation. So I can sort it by which ones students were experiencing the most often here at opportunity number 12. And it was this finding the scrap metal area related to question 1 in this problem. And we have this nice feature that you can go see what that problem looked like. And now this depends on whether the provider of the data has provided information about what the problems look like. But for Open Learning Initiative courses and for our cognitive tutors, we often have this information. In this case, it actually is pointing to a design document that we used in building this tutor. And here's this POGS problem that's asking what happens when the POG is cut out of this metal square, how much scrap metal is left. And students are filling in this table down below. And it's this 4.43 that they have to figure out. This table comes to them originally just with 3 columns and the 3 question rows. The 4th and the 5th column here, the area of square and area of the POG are not present when they first see it. And they have to figure out these values, and figuring out that the radius of the POG is 2 is easy because that's given, and that the length of the square side is 4, that's easy. But students often struggle at this point because they don't have a formula for the scrap metal, right? So they have to figure out how to, in this case, that they ought to compute the area of the square and then the area of the circle, and then subtract them, and they'll get that answer. And if they ask the tutoring system for help, it might suggest that they add these extra columns and fill in those values. But what we were looking at here is that this particular step is especially hard for students. So if we go back to this learning curve, that's that particular step. If we go forward one here to this data set, we see this is scrap metal area question 2. That's basically the same mathematics, right?
Mhm.
But it's way easier. And if we go one more forward, here's another quick case. This is scrap metal question 3. That's the last one, and that's really easy. So how come, even though they're doing exactly the same mathematics in all 3 cases, the first one's way harder than the second and the third? Now, I don't know if that strikes you. How about folks in the room? Is it? Does that
Something
seem
else
odd?
is going on there.
Something else is going on, right? Yeah. What could it be? Are doing geometry problems more than about doing the arithmetic?
Sometimes.
Hopefully, because they've already had a class on arithmetic, right? That part shouldn't be hard, right? The hardest part for these problems is coming up with the plan, right? It's figuring out that the way I'm going to get this solution is I can't just use one formula. I need to use 2 formulas and put them together. And once you come up with that plan in question 1, you just reuse it in question 2 and question 3. So what we see that in these hard, easy, easy, or if you go back to 1, 2, 3, the same thing was more or less happening here: hard, easy, easy, hard, easy, easy. So that's one thing that was going on. Turns out another thing that is going on, which goes to this age-old question of when is scaffolding a good idea?
Right.
So let me show you here on the step just before. It's a lot easier. And if we drill down on what that problem was, on the surface, this looks like a pretty similar problem, right? Maybe it's easier because the circle's already inside of the square. It turns out from other problems, we can tell that that's not what's making it easier. What makes this one easier, as it turns out, is in this table, all of these columns were given at the beginning, and the unwatered garden part, the irregular shaped part, is at the end. Whereas the square and circle are being asked for first. In this other one, remember these 4th and 5th columns weren't present in the interface at first. So there's no scaffold or clue there, as there is in this question. This question's cluing the student in. Oh, maybe my square formula and my circle formula are relevant. So the only part of the plan they have to figure out is, why did they ask me to do that, and how is it relevant, right? Whereas in this POG's case, they don't have those clues. And this one's much more like what we want students to do, on the real world, is, meet a complex problem for which a point solution doesn't work. Can you bring different formulas together to solve those? So we were able to identify those 3 different, they're essentially the same arithmetic, but 3 different circumstances. Repeating a plan I've already figured out, actually having to plan, or having to plan, but with a big help, a big hint, right? So if, as Kim said, you relabel this exact same data, now instead of 1 skill with 3 skills, I'll show you what that looks like here. So I'm going to pick a second model that'll show up in the green line. That tracks the data much better, because we're making this distinction between these 3 kinds of problems. And if we go into Datashop's performance profiler, is another way to see this more clearly. We can pick this particular original knowledge component and see all of the problems and all of the steps and all of the problems where it was used. And you can see there's this big variation in error rate. And the old model that was assuming these are all the same skill, that's the blue one here, essentially makes the same prediction about all of them. They're all about the same. Like if you know the skill, you get it right. If you don't, you get it wrong. The new model has 3 different distinctions, and you can more or less see 3 different lines here. And while it's not a perfect fit to the data, it's a much better fit to the data. So we've got an insight. The end of the story is we redesigned this tutor so that we gave students more practice on just that planning phase. And we actually did this with multiple choice questions, so it wasn't super sophisticated instructional design in the sense of the technology, but in the sense of saying, what if we just ask students to, here's a problem, which of these would be a good plan to solve it? You don't have to do the arithmetic. We would just want to see if you can recognize the good plan or evaluate which plan is a good one. And by doing that, they get better at solving these kinds of problems, and they do so in a lot less time. So I hope that second example helps you see how this works. And you know, if you have data like this, or you don't want to use an OLI course like that generates data like this, you can use a technique to really find out where students are struggling and redesign the course to make things better.
Thanks, Ken, for showing us that in Datashop. So just to kind of summarize here, when you see these, what you're looking for from a learning curve is the error rate going down. And when you don't see that, then it's an indication that you need to dig in and figure out maybe there's something going on. Maybe there's more scaffolding needed. Maybe the questions are too easy. It's assessing too much prior knowledge. Those are the types of things you'd be able to figure out by looking at these learning curves. So to the audience, how are you feeling about learning curves? Do you have any questions? Was that another good example and a nice show of Datashop, or do you have reservations at all?
Hello. So I was just curious what the data behind the analyses looks like. Like what does the data set have to look like in order to use something like that?
Yeah, that's a great question.
Do you mean what do the interactions look like that students are engaging in that generate the data, or what do the data tables themselves look like?
Yeah, so I was actually going to ask both of those questions, but the first question is, what do the data tables themselves look like?
Oh, okay. I guess I prematurely stopped sharing because I'll show you an example in Datashop here. Sharing back on. As with lots of documentation, there's a rich set of Datashop documentation that people don't always look at. In here there's a section here on learning curves that has some particular illustrations of it's descriptions of how they work. And if we back up a bit here to, I'm actually trying to remember where this is, to be honest. There's descriptions of the problems here. What do KC models look like? I know it's here. Where is it? Maybe is it in this format section? Well, this gives you a sense of abstractly for, we have in a table a student identifier that's anonymized, an anonymous student identifier, a timestamp, I'm going to just skip to some of the more critical ones. There's a sense of the level of the curriculum the student's at, and maybe a problem or the name of a problem or activity that they're working on. There are specifics about what particular interaction they're having in the computer interface they're working on, and what outcome there is. If it was a question, which a lot of this data is, or a step in a multi-step problem, was it correct, or was it an incorrect action, or did they ask for a hint? And then there is this knowledge component tag that may be on the data as it comes in, or you can add once the data is there. And I guess concretely, to go back to this data set, I can show you what one of those tables looks like within that data set.
What's the minimum amount of data that they would need, or the minimum column? So they would need outcomes tied to questions and the answers for those questions.
Yeah, basically, sometimes we say the 4S. You need student, you need the skill. It's nice to have, we say step, but a label for the item. So what student is doing what item, what's the skill level, and were they successful or not? Mm-hmm. That's the minimal. If you had those 4 columns, you can do a learning curve analysis. And the skill column, or equivalently knowledge component column, you could have more than one of those. And with that, the system will have to generate. So here I'm showing one of those more complete tables. And Aaron, your question is good, because it doesn't have to be this complete. This is just showing more of it. But here, anonymous student ID is one of those. The problem name and the step name are essentially indicate the level at which we get an observation of students' performance. This is indicating which attempt, if it's a question they can try multiple times, whether they got it correct or incorrect in the outcome column is basically the success thing. And then you'll see over here, what one KC model in this domain is everything's geometry. It's actually interesting to look at that learning curve, because you can very well see that it's not just, do more geometry, learn more geometry. The error rate goes all over the place with that particular knowledge component model. Here's the original model. And you can see this one we've got labeled with lots of different knowledge component models. Mm-hmm. Yeah, but the Datashop will generate the x-axis in the learning curve is the opportunities that the student's seen that.
Yeah.
And that can be generated from those 4 columns I indicated, or that can be, part of the import.
And so the opportunities, if it were a part of the import, then is that something that you indicate, like this was opportunity 1, or is it like indicated by what, and you said levels as well, that it's like level 1, 2, or 3, or is
yeah,
it
well, one of the reasons that we have the time in the usual import is we can use the time, right? So you can sort the data by student and by time and by knowledge component and by time. And then when you do that, then you just, within each student knowledge component set of rows, if they're ordered by time, you just go 1, 2, 3, 4, 5, 6, right? And then
awesome. Okay.
Yeah.
And then, so Datashop can then take those times and enter them into opportunities? Is that,
yeah, exactly.
Okay. Okay. It's just curious what it's doing over there.
Yeah. So in fact, if you're doing what Kim did and you want to try to, improve the model, you can export a table that'll come out in Excel format like this, that'll show just the items that need to be tagged, and whatever existing tags are present will appear in this table. And then you can add a new column that retags. Typically what I do is I copy the existing one, because most of them are going to stay the same. What
right.
Kim did, right?
Yeah.
And she's going to take subset of columns, like in my example, this composed by addition, there's some 20 rows in that were labeled composed by addition. And 5 of them got relabeled just plain arithmetic, and 5 got genuine planning label, and these numbers aren't right, but it's say 10 were the scaffolded planning. And then I won't let this run. Then you come back and you import that table. Datashop will then redo the opportunity counts and recompute the learning curves and all the statistics. And the new model will get placed in this is kind of a leaderboard of the knowledge component models, showing the ones that essentially have the best prediction fit against the data are up at the top here. There, there's technical details in whether we use the AIC, BIC, or cross-validation metrics, but if the new model's better, it'll be higher up in this list.
And then when you go to the learning curves, where you showed them, you can pick the different models when you're in the line graph area, when you click on all data.
Right here.
Look at your learning curve and see, whether it's improved based on your changes.
Yeah, like this one shows, what if we treat this all as one skill? Does the error rate go down?
The geometry skill?
Yeah, it's all geometry. You get better at geometry, right? And obviously when you go from, say, square area to circle area, it gets harder again, and then you go to trapezoid area and it gets way harder, right? And in this curriculum, it wasn't completely blocked like this. The tasks were interleaved, and so what you end up, the relabeling does is, like, this one might be the first opportunity for trapezoid area. Maybe this was the second, but maybe this is the third, right? And so the system will, when you relabel and get them sorted, as it were, will then, convert. This is all stretched out, right? When I show the one of the better models, you can see that it's more collapsed now because there's more skill, and so fewer opportunities for each of them, rather than lots of opportunities for that one imaginary geometry skill.
And so when you're creating these new models, is the only thing that you're doing is relabeling the knowledge components, or are there other changes you're making too?
Well, that's here in Datashop, that's the only thing you're doing, at least with this particular set of tools. If you want to play with the statistical model, that's possible, and that is part of what we've been trying to facilitate in this LearnSphere project. And I guess we'll be talking about this a little bit more in an upcoming webinar. But yeah, there is a particular illustration in here of a workflow for comparing different learning curve models. So in Datashop, we use a version of logistic regression, which we call that AFM, or additive factors model. And all that wonderful documentation explains how that works. It shows you the R code that implements it. But another one that's used in a lot of adaptive systems is called Bayesian knowledge tracing, and BKT. And this workflow will allow you to import one of these data files and then apply one statistical method to generate learning curve visualizations, and a different statistical method to generate another set of learning curves. And then you can go in and inspect those learning curves and see how they compare. And I guess this workflow hasn't been run, so we won't see anything at this point. But yeah, I mean, in general, you can change both. We built Datashop to focus more on this exploring the knowledge component model. But there's certainly other very interesting questions. For example, around what if you allow the rate at which individual students learn to vary? That's not part of this particular model. This model assumes, actually for pretty good empirical reasons, that the learning rate is reasonably the same across students when we're talking about learning rate in terms of these quality opportunities to learn. It's actually it was quite surprising to me to see how regular the learning rate is. Where students start, whether they're at a 70% error rate or a 20% error rate at the beginning, that varies a lot. But how much they move per opportunity to practice, it's surprisingly regular across a lot of different domains. Maybe that's good news for
it sounds nice.
for equity, right? Yeah.
Right.
Okay, did anybody else have any questions? Because I know I had another question.
And by the way, feel free to throw in questions in the chat if you have another question. We can process them in parallel.
Yeah.
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 Go for it. Is it Cassie?
Okay. Yeah, it's Cassie. Yeah, so my next question was, of course, that other question that you asked me before is about the interactions that the students are having themselves. So the example that you shared with the geometry data set, that was from a cognitive tutor. And then the example that we saw first, is that from a different kind of course? Was that from like an OLI course or?
That was from an OLI course.
OLI.
Okay.
It's just a regular, selected response question.
Oh, I know where it is. It's here. Here we go. Here's a little video of that particular cognitive tutor. Or is that just a screenshot? Yeah, that's just a screenshot.
There's a video.
Oh, great. It's in Flash, so of course it will work forever on the internet or not.
Oh gosh.
Yeah. It used to be a video. Yeah. This actually shows the problem when it's completed, but the design document I showed you earlier didn't have as much color on it, but it's equally static, unfortunately. But if you're typing these values in 4 and 8, I think in this video, the student, I don't know, does 8 minus 4 and types 4 in here, and it turns red, and then they go. They ask for a hint, and the hint says, "Why don't you add columns for the square and for the area of the square, or the area at the end of the?" And so they go do that. They type in these labels. They compute it. They come back here. Maybe they ask for another hint. It says, "Well, now that you've computed those values, why don't you subtract them?" Kind of thing. Actually, the hints are more graded than that. But that's basically the kind of data. So there's essentially for each step, which is in this particular interface amounts to a cell. There could be multiple actions or transactions. It could be an incorrect action, a hint request, or eventually a correct action. And all that's being logged. So in the learning curves, we're seeing if the student is getting it right on their first attempt. So yeah, if we were to go to an OLI data set, I think we could similarly see, maybe I have, how about e-learning design principles? This is from my e-learning course. Actually, I'm not sure we have the problem data connected to this particular course. Here, it depends on the contributors of the data, whether there's this problem list. But this is the list of all the problems in OLI. Is this going to give me? Yeah, here's. So for the learning objective below, identify the following components of a good objective according to the ABCD method. I don't know if you know this method for specifying a good learning objective. So, given a standard sentence, the English 101 student should be able to identify the noun and verb without an error. So identify noun and verb is the behavior, maybe? They actually can, I guess you can do the item here, but that was kind of weird.
So this is your course, right?
Yeah. Yeah, so yeah, you can see that in this case, the data is, more of a traditional formative assessment. Here's one with check boxes. Here's another one with menus. There are some drag and drop activities. Oh, here's a so-called submit and compare, where they're writing an open-ended explanation. In this case, there's no automatic correct or incorrect, because we just do the comparison on their own. But yeah, going back, this is another example of a domain that's not a math domain. This is basically an instructional design class, and the learning curves on the formative assessments actually look surprisingly good, because in this case, usually what we find is that when we just code by learning objectives, we get okay learning curves, but they have a lot of blips like the one Kim showed. And it is true that some of these, like this one, that one doesn't look very good. It's partly because of multiple select items, which is something we got to work on. Not because multiple select items per se are harder, but because of the way we're scoring. Like, yeah, here's one. And that one on average is going down, but there's some roughness there. So there's probably more going on than distinguishing types of
Learning and cognitive load?
With respect to cognitive load, yeah. You want to see one of those items?
Sure.
I'm scared. Oh, that's a submit and compare. What is instruction? That's a good one.
I think it's one of the, this is one of the reveal. So
yeah,
we compare, and then you.
Yeah, we do submit and compare, but after or before the comparison, we ask, after they've typed in an answer, we say, which of these options is like your answer?
Yeah.
Oh, that's really neat.
Yeah.
And then it goes down further, and then they get the
So
answer.
an observable manipulation intended to change the learner's experience is the CLE framework's technical definition of instruction. Yeah. So they're supposed to check that, and that'll be what's going into this learning curve. Whether that one was harder, I guess. Well, I'm not sure I was tracking the exact right step on that one, right, Kim? Is that what you were pointing out?
I think the last step is the actual answer to the question. The second one is, were these in there? It is tracking that one, and then
so
the last one is the actual answer.
6I1.
Yeah.
So 6I1. What?
No, it's down further.
Yeah.
It's down further.
Yeah. So
Kim knows how to read these better than I do. Still further. Search for 6.
Yeah.
Well, part of what we're trying to do with the Open Simon effort is, we've made some progress on making this easier to do. It's still not always that easy. So what we hope is, other folks can jump in, either, help tell us how to make it easier, or even go to the source code and re-implement it so that it is better. Yeah. But part of this particular challenge is coordinating, there's the course design in OLI and all the labels that are used by developers to label the items internally. And that gets passed to the database, right? And then, and then we see those, essentially made up variable names for these problems and steps. And it's like,
right.
Is it interpretable? Kind of, sort of, but yeah.
That is the agent one. It is that question. It's just further down. But
Oh, it must be this one.
Yeah.
Yeah, okay.
So yeah, what you're saying is just similar to, the domain of the causal modeling course. If you're working on the course, you're going to know these questions. You'll be able to identify what that was. I know where this is. I know this question because I did the coding on this.
Right. Yeah, that's right.
Right. So yeah. So when you're working in a collaborative team,
designer or the learning engineer who's doing this work, they will know that. Of course, our goal is ultimately that instructors can be doing this, right? And they can WYSIWYG author questions, and then they can go and click through the data and find these opportunities to improve, and write new questions, put them in, and boom.
Yeah.
We do have another question in the chat. And it's about the difference in student performance when a CTAT tutor is implemented in an exam setting versus experimental setting, and how in an exam setting, your students are penalized for using hints, but in an experimental setting, they're not.
Well, this is a good question. I guess it raises a number of issues. By an experimental setting, if you mean during the learning or during the instructional phase, when we're drawing learning curves during the instructional phase, we're treating hint requests as errors. So, I don't know, penalized is a kind of potentially loaded word, but indeed, we can see, for example, if we go to the performance profiler, this shows that this particular problem explain how steps in difficulty factors assessment implement the big picture of instructional design. To expand that a little bit, that was pretty hard. The red here indicates the error and the yellow is the hint, right? And this is on their first attempt. Now, of course, they get multiple attempts, and we hope they eventually get it right. They learn from it, and then the next time they're able to do it, correctly without asking for a hint. But a related issue is a summative assessment versus a formative assessment. And sometimes on summative assessments, we don't give feedback. And then the question becomes, should you increment the opportunity count if the student hasn't gotten feedback, right? Or is the next question on the same KC basically at the same point in their learning process because there hasn't been any intervening instruction. So yeah, on summative assessments, we have explored, does the model work better if we don't increment the opportunity to learn count during the summative assessment? I think we haven't done enough of that. I'd say the jury's still out. As a matter of fact, we're one of my programs working on a way in Datashop to indicate when something is merely an assessment event but not an instructional event.
I see.
And if you make that indication, then this automatically computed opportunity count won't increment if it was merely an assessment event without being an instructional event.
I see.
Because this has both of them in there right now.
Well, this assumes that everything's both. It assumes that students are trying on their own first. So that first attempt's the assessment event. And then if they get it wrong, they get feedback. They can ask for a hint. They might try something else. They eventually get it right. All that subsequent activity are instructional events. Hope learning occurs. And then we see that at the next assessment event.
Okay.
The next time they see hopefully a different question for the same concept or skill.
Okay. I just have one more question regarding the instructional design example that you showed, Ken.
Yes.
So in the instructional, so I saw some open-ended questions in the. So what kind of analysis can you do with such open-ended questions? Because I mean, it's not like math where there is a correct answer and a wrong answer. So what kind of analysis would you do in the instructional with such open-ended questions?
Do you have a TA?
No, but yeah. Okay.
Well, yeah. One version of that is you hand grade it. Either you, the instructor, or your TA, or another version is peer grading, and then there are techniques that look at whether which peers are more reliable as graders, and then you can trust their grades more than the less reliable peer graders. And then of course the obvious AI go-to is you have a natural language understanding system, and we've done some of that through some statistical natural language processing methods. That usually depends on having a bunch of answers that have already been graded, and then you
I see. Okay.
learning system to replicate that grading. Yeah, the really hard thing to do is to make a knowledge-based natural language understanding system.
Oh.
Yeah.
Uh,
We actually did that for,
uh-huh.
and this data set is buried somewhere in here, for geometry. One of our PhD students a number of years ago
Uh-huh.
built a system where students were asked to explain, how did you know that third triangle was 70 degrees? And they're supposed to say, the sum of the angles of a triangle are 180. And if they would say, the angles of a triangle are 180, the system would come back and say, all the angles are 180?
Oh, I see.
And so it was a dialogue-based system that could actually categorize the student's explanation as missing a feature, and then feedback that pointed to that feature.
Okay.
Yeah, but that was that was like a 2-year intensive thesis effort.
Oh, all right. Okay. Not.
Yeah.
But another way is to follow up with machine readable questions, right? Like,
oh yeah.
Which is what we
Great
did
point.
here, the
Right.
reveal questions.
Yeah,
So
we've been using this strategy as we look at that data, and see what the common wrong answers are, and then we create a multiple choice question
I see.
that uses that wrong answer. Or yeah, even as you saw here, even before anticipating that, here, this is the open-ended.
Yes.
And this says, which of the following does your answer include? So now give them the opportunity to say it in their own words. And it's kind of up to me to go in there and check whether they, of course, some students are typing ASDF, right? It's the letters on the keyboard in a row. Right?
Yes, yeah.
And then they're going down here. But some are genuinely trying here, and at least we're giving them an opportunity to try to do the open-ended. And if you spot grade that a little bit, you can encourage them to really do that. But then they get the feedback here.
I think they even get one more question. Can you scroll down to see?
Got it. Okay, thank you.
That question is the actual, which ones do you think are part of the correct answer? So what did you have?
Oh, right.
And this is where we actually get the score.
Oh, right. We don't, this one doesn't, we don't score them on.
No, we score them
We're
on the
sitting on this data, actually. Like, how good are they at self-assessing? Yeah. But, we haven't analyzed whether what they say is in their answer is actually in their answer.
That would be an interesting little.
It would be.
Yeah.
And probably, I mean, that the literature I know on this sort of thing is novices don't see things that experts do, such that they might think they have something that isn't really there, or they might not notice something that they do have there.
It looks close enough, which is part of the problem we've always had with open response if they're not graded.
Yeah.
That's right.
All right.
Yeah, I got that.
Ready? Thank you.
You're welcome. Well, we're just about at time. Does anybody have any other questions? I want to make sure everybody has a chance on the line to get their questions in.
There are some instructional videos. I guess Aaron pointed to some of those that show you that, if you want to go through this slower and try it out on your own.
And actually we'll be following up with an OLI module as well that will, first of all, check, help us gather some data on how well we did in explaining learning curves. So there's some questions in there, knowledge checks for you all to complete. But then we'll be expanding that out in the coming weeks to include some actual instruction on learning curves and Datashop use. So look for that.
You mean LearnSphere?
LearnSphere. I'm sorry.
Yep.
So it's a page with some questions on it.
Right now.
Module will be a little extreme.
Okay. It's within a module, but it's just a handful of questions just to see how good we did and to help us collect data, but then also to get you access to the more instruction we build into that as well. So know that I'll be following up with that. And if there's no more questions about learning curves at the moment, then I will, let's see if you want
if was it Cassie still wants to see this video, there is in this video has the video of the student system in here if you want.
Oh, great.
Yeah.
Thanks, Ken. So know that our next webinar will be more in depth on LearnSphere, and it's on October, let's see here, I have a slide about it. October 16th. And there's the website to get to our list of webinars and to see what the upcoming topics are. So thank you all so much for joining us. This has been really great. Thanks for your questions. They were very, very good questions and got us into a nice dialogue about learning curves. So thank you all and enjoy the rest of your day. And hope to see you next time.
Bye.
Bye.
Thank you.
You're welcome.